In this last section that we're looking at from chapter 4, we're going to be working on solving equations with what we know about logarithms and exponential functions. Now, always remember to work smarter, not harder. There are going to be more than one way. There's going to be more than one way to do each of these things. Make sure you do your best to choose the easiest method to solve. Now, if you don't choose the easiest method, that just means usually more steps. But I will give you some good places to start with. Okay, so first of all, we're going to talk about the one-to-one property. The one-to-one property is great. Anytime you can use it, this is the quickest and easiest way to a solution. This property applies both with exponential functions and logarithmic functions. It works very similarly in each of these two inverse operations. If you're dealing with variables in the exponents, the one-to-one property tells me that if the bases are the same, then the exponents are equal to each other. So in general terms, if I have base b raised to a power and base is equal to base b raised to a different power, then that means that those exponents have to be equal to each other. So here's a more specific example. If I have base 2 on each side of the equal sign and that's all I've got going on, then I can say that those two exponents are equal to each other and I can solve for the variable. I can solve for x here. Once I apply the one-to-one property and set the exponents equal to each other, all I have to do is finish solving. Oh, I'm writing out answers in my head. All I have to do is finish solving for that variable. So I've got 4x equals 8, and then I divide by the coefficient 4, and I get that x equals 2 is going to be the correct answer. Now go back and plug it in and make sure that we're comfortable with that. 2 times 4 is 8, minus 1 is 7. 2 to the 7th equals 2 to the 7th. That's true. If I have a logarithm that I'm starting with, when the bases are the same, then the arguments are equal. So, and I didn't give a general example here, just a specific example. Natural log is equal to natural log. All I have on each side of my equation is the natural log statement, so they're both base e. Since the bases are the same, I can set those arguments equal to each other. And then I solve from there. Now we're going to go ahead and solve for x because this is going to be good practice. Anytime you have a variable in numerator and denominator, your go-to move is to multiply both sides by that denominator. When you multiply by the denominator over here on this left side, anything over itself cancels out, so that leaves me with just the numerator, 7x minus 23. Now on the right, I have to FOIL that. I have a binomial times a binomial. So when I FOIL that, I multiply it together. My first product is x squared, my outside product is 1x, my inside product is negative 3. Well, 1 minus 3 is a negative 2x, and the negative 3 times 1 is minus 3. So over here on the right, I see that I have a quadratic equation going on. So I need to move everything over here to the right so that my squared term stays positive. So I have it set equal to 0. And now I want to factor. Oops, that's minus plus 20. Now I want to factor. When I factor that quadratic, I'm just going to break apart. The constant is positive, so my signs are the same. My middle term is negative, so that means both of these are going to be minus. Factors of 20 that add up to give me 9. Well, 4 times 5 is 20, and 4 plus 5 is 9, so that works out. Then I use my zero factor property and set each of those equal to 0 to see what's going to make this a true statement. And I get proposed solutions x equals 4 and x equals 5. Now remember, we've got some definitions. As part of our definition of logarithm, we have some requirements for our argument. Our base is going to be positive, so that means that our argument is also going to end up being positive. So I need to go back and I need to plug each of those values into my argument just to ensure that my arguments are going to remain positive, and they do both work here. Okay. We're going to do a little practice with this one-to-one property. We're not going to do all of these together. We're just going to do that first column. And then the second column, if you, I encourage you to use as practice on your own. If you have a class with me in person, then we will work on those in class together as well. All right, one-to-one property means I need the bases to be the same. So I need to figure out how to make both of these base 2. Well, 2 to what power gives me 64? 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64. That's 6 times multiplying 2. Now that my bases are the same, I can say that my exponents are equal and it's solved. Same thing here, I can rewrite these both with the same base, base 5. Well, 5 to what power gives me that 125? It's going to be 5 cubed, so x equals 3. Since the bases are the same, I can use the one-to-one property and say that the exponents are equal to each other. The next one, again, I'm going to go to 2 with my base as my base. 2 to the 5th power is 32. This time, when I set my exponents equal to each other, I still have a little bit of work to do. I need to finish solving for that x. So I'll add the 1 to both sides and then divide by the coefficient 2 so that I get x equals 3 again. Let me change colors, mix it up. All right, so here I have a choice. Now I can go to 4 actually and leave this as 4 as my base over here. If I don't see that, I could go all the way down to 2. Let's look at it using 4 as our base. If we do 4 as our base, 4 times 4 is 16 times 4 is 64. So that would be 4 cubed on this right side. And then I have 2x minus 1 equals 3. Add the 1 and I get 2x equals 4. And then when I divide by that coefficient, I get a result of 2. To double check, 2 times 2 is 4, minus 1 is 3, 4 cubed equals 4 cubed. Yep, we're in good shape. Now what if I hadn't seen that needed to be, that I could use the 4 as my base? Well, if I don't see that I can use the 4 as my base, then I could have made it 2 as my base. Now, if I do that, it takes a little bit more work. We already figured out that 2 to the 6th power is 64, right? We figured out that 2 to the 6th power is 64. So this right side would be 2 to the 6th. The left side, 2 squared is 4. What's important here is that I would need to make sure that I put the exponent I already had in parentheses, because I would then have 2 times that exponent. Now that would give me 4x minus 2 equals 6. Which still gives me the same result of x equals 2. Okay, so 2 different ways to approach that problem. On number 9, I can't raise 8 to a power and get 32, so I'm going to need to go to 2 as my base for each side. 2 cubed is 8. 2 to the 5th we figured out is 32, so that would be 5 times the x that was already there. Well, why didn't I put that in parentheses? I could have, but there's just one term, so it's not going to affect it if I didn't. So when my bases are the same, I set my exponents equal to each other and I divide by that coefficient. I get x equals a rational value of 3/5, a fraction. Number 11, 9 to the x equals 27. Again, I can't raise 27 or 9 to a power and get 27, so I need to go to 3 as my base. 3 squared is 9. 2 times x is just 2x. 3 cubed is 27. Now that my bases are the same, I set my exponents equal to each other. It's my one-to-one property. And then finally, this last one, 3 is good. I can make this 3. So 1 minus x is my exponent here. 3 cubed is 27. 3 to the negative 3 is 1 over 27. There's my negative exponent coming into play. One-to-one property, bases are the same, so I set my exponents equal to each other. If I subtract 1 from both sides, I get negative x equals a negative 4. I can't leave it a negative x, so I would divide both sides by a negative 1 so that I get x equals a positive 4. Alright, and then like I said, we're going to leave that other column for you to practice on your own, or for you to do in class. Okay, so we have choices as we're deciding how to solve equations with logarithms and exponentials. If I can, I'm going to use that one-to-one property that we just practiced, because it's usually quick and easy. If I can't use the one-to-one property, I want to see if I can use the definition of logarithm. Now that definition of logarithm tells us that we can switch back and forth from log statements to exponential statements. This works when I have a variable in only one exponent. So let's solve for this. I cannot raise 2 to a power and get 10, so my one-to-one property doesn't work. So I'm going to use my definition of logarithm and rewrite this in log form. So I've got log, well, my base here is 2, my exponent is x, and my argument is 10. So my definition of logarithm tells me I can rewrite this as an equivalent log statement. I don't have a base 2 button on my calculator, so I'm going to need to use change of base. Remember, you can do common log or natural log. It doesn't really matter. The number that is the base goes on bottom. When I plug this into my calculator, let's go ahead and round to 4 decimal places. You plug that into your calculator, you should get x is equal to about 3.3219 rounded off. So that's what to do if we have variable in one exponent. Now, if I have a one log statement, then I'm going to use the definition of log again. Only this time, since I'm starting with a logarithm, I'm going to convert it to exponential form. So right here, I've got log base 10 because it's common log. X minus 3 equals 4. Can't do anything with that with x in the argument. So I'm going to convert that using the definition of logarithm. My base here, common log, is 10. The answer is the exponent. And the argument then is x minus 3. Well, 10 to the 4th power means a 1 with 4 zeros. I add 3 to both sides. And I get 10,003 is equal to x. What if there's more than one log statement? Well, if there's more than one log statement, I'm going to use the properties of logarithms that we talked about in the last section, where we can expand and condense. That's an O, sorry. Properties of logarithms. We're going to expand and condense. Only this time we hopefully are going to condense so that we can get just one log statement on each side. Alright, over here on the left we've got 2 separate log statements, both base 2. They're being added together. My product rule, addition pairs with multiplication. So I can say log base 2 of, and then I multiply my arguments together. X times x plus 2 is x squared plus 2x. That's equal to log base 2 of 6x plus 1. Now I have a single logarithm on each side. They have the same base, so I can apply my one-to-one property. If the bases are the same, then I say that the arguments are equal. X squared plus 2x is equal to 6x plus 1. Anytime I see that quadratic, I want to set it equal to 0, keeping the squared term positive. So I'm going to move both of these values to the left. Now when I look at this, 1 is prime. 1 times 1 is 1. Negative 1 times positive 1 is negative 1. There's no way to end up with a 4x in the middle. So this is not factorable, which means I'm going to have to use my quadratic formula. So x equals negative b is going to be a positive 4 plus or minus square root of b squared minus 4ac all over 2a, where I've got a, b, c. And then I need to clean this up. So 4 plus or minus square root of negative 4 squared is 16, and then a negative times a negative becomes a positive. So I've got 16 plus 4 is 20 over 2. Square root 20 is it's not going to give me a nice rational value, but it is going to simplify. I knew it wasn't going to be rational because this was not able to be factored. So 20 is 4 times 5, so that's the same thing as square root 4 times square root 5, and the square root of 4 is 2. So plus or minus 2 square roots of 5 over 2. I need to simplify that as much as I can. I'm going to keep it exact. 4 over 2 plus or minus 2 square root 5 over 2 gives me 2 plus or minus the square root 5. So I've got two separate proposed solutions, 2 plus the square root 5 and 2 minus the square root 5. Because these are my arguments, I need to be able to check and see if they're going to be valid. So I need to see, okay, 2 plus square root 5 is about what? And 2 minus square root 5 is about what? I'm confident that 2 plus square root 5 is going to be okay because it's going to be positive, right? 2 plus the square root of 5 comes out to be about 4.236. What about 2 minus the square root of 5? 2 minus the square root of 5. Oh, that comes out to be a negative 0.236. So are those both valid solutions? Well, my positive value is fine when I check it in all three arguments, but this negative value, it's not going to fly right there. I can't have a negative argument. So that is extraneous. And I only have one valid solution. Okay, let's look at another example. Oh, what if I have, that was if I have more than 2 log expressions. What if I have 2 exponential expressions and they have different bases? Well, if that's the case, I'm going to take the natural log of both sides. Now, you could take the common log, but just if we always stick with the natural log, then it's easy to talk about it that way. 7 and 5 are my bases. I can't use my one-to-one property. There's no way I can write those in terms of the same base. So I'm going to say, okay, well, natural log of 7 to the x minus 4 is equal to natural log of 5 squared. The next thing I'm going to do is apply my product rule, where I take my exponent, or excuse me, my power rule. I'm going to take my exponent and pull it out front. So I have x minus 4 times the natural log of 7 equals 2 times the natural log of 5. And what am I going to do next? Well, let's move this natural log 7 over to the other side. So I have x minus 4 equals 2 times the natural log of 5 divided by the natural log of 7. What do I need to do to finish solving for x here? Well, to finish solving for x, I need to add 4. So x is equal to 2 times the natural log of 5 divided by the natural log of 7, and then I will add 4 to that. When I plug that into my calculator, I need to make sure I use my order of operations well. 2 natural log 5 divided by natural log 7, and to that I add 4. So my result comes out, if we're still rounding to 4 decimal places, 5.6542 is my approximate answer. Alright, now we've got a little bit of practice to do. We're going to talk about how we can pick the best way to solve. Remember, I said there can be more than one way to solve an equation. You try to pick the one that's going to be the easiest. I see that I only have one exponent. My first check is to see if I can use the one-to-one property, but I can't rewrite these as the same base. So I'm going to use my definition of logarithm. I'm going to rewrite this as a log statement, log equation, to get that variable out of the exponent. So I've got log, my base is 3. My answer is the exponent, so the argument goes here. Log base 3 of 17 equals x. Well, now I'm going to use my change of base. Remember that base number goes on bottom. And this time I'm instructed to round to 3 decimal places, so if I plug that into my calculator correctly, it should round off to 2.579. Number 2 over here. Again, I have exponential form. I cannot use one-to-one property because I can't make those bases match. Since I can't make the bases match and I have variable in 2 different exponents, I'm going to have to take the natural log of each side. Let me do a different color over here. Natural log of each side. So using my power rule again to bring those powers out in front. Now last time I only had one variable, and so I just divided out this natural log. Here I have the variable on both sides. So instead of dividing out the natural log, I'm going to distribute multiplication across that addition on both sides. And then I see that I have 1, 2, 3, 4 terms total. 2 of those terms have variables and 2 do not. I'm going to get the terms with variables on the same side of the equation. So let's go ahead and just move this one over here. So when I do that, these are not, don't have the same natural log, so I can't combine them in a single term. So I've got 6x natural log 5 minus 4x natural log 2. Now on the other side of my equation, I need to move this term, the terms that don't have an x, to the same side. So I'm going to add that plus 3 natural log 5 over here. So this is natural log of 2 plus 3 natural log of 5. Again, not the same argument, so I can't combine them into a single term. I'm trying to solve for x, that's my goal. So on the left side over here, I'm going to factor out this x as my common factor. So x times 6 natural log 5 minus 4 natural log 2. To solve for x, I need to divide both sides by all of this. 6 natural log 5 minus 4 natural log 2. Now this is the expression that gives me my value for x. The key is to make sure that I put that into my calculator in such a way that it comes out correct. My recommendation to you, if you're not going to hit enter a bunch, is to make sure you use parentheses. Parentheses around the numerator, divided by, and then parentheses around the denominator. What should come out here is a value of x of about 0.802, 802 thousandths. Alright, let's kind of divide this out. Here we've got e to the 0.1x equals 11. Well, I've got one variable. I can't make the bases the same, can't use my 1-to-1, so I'm going to use my definition of logarithm. Here I took the natural log of both sides. Here I'm going to use the definition of logarithm. I'm going to write it as a log statement. Log base e is natural log. Natural log of 11 equals that exponent 0.1x. I can plug that into my calculator. To finish solving for x, I just need to take whatever this is and divide it by a tenth, divide it by 0.1. So to see that in your calculator, natural log of 11 divided by 0.1, 23.979 is going to be what that would round to. Alright, what about this one? We've got a single log statement. The variable is in the argument. I need to solve for it. I can't solve for that variable while it's in the argument, so I need to use my definition of logarithm again. Instead of log form, I'm going to rewrite it in exponential form. 2 to the 5th is equal to that argument. Well, what is 2 to the 5th? 2 times 2 times 2 times 2 times 2 is 32. And then I just need to solve for x. So I'll subtract 1 from both sides and then divide by that coefficient. X is going to be equal to 31 divided by 4. And I'm going to leave it like that. If you do 31 divided by 4 in your calculator, it comes out to a nice decimal, 7.75. But unless you're told to change it to decimal form, go ahead and leave it as an improper fraction. Alright, next 3. I encourage you to pause and do these on your own and see how you do. If you get stuck, then restart the video because I will be working through. Here I've got 2 log statements, so I'm going to use my properties of logarithms. Addition pairs with multiplication. So I'm going to multiply the arguments, x times 4x minus 1. And then I'm going to use my definition of logarithm to rewrite this log statement in exponential forms. My base is 5, my exponent is 1, and that is equal to my argument. Well, 5 to the first is just 5. This is squared, so it's quadratic. I need to set it equal to 0 and keep my squared term positive. So I need to move that 5 over to the right. To solve, I want to factor, and this one will factor. 5 is going to be 5 times 1. I've got this 4 to deal with. Actually, if I leave that as 4x instead of trying to do 2x and 2x, I don't want to multiply the 4 times 5. I want to multiply the 4 times 1. So I've got 4x and 5x. I need a negative 5x in the middle. And this negative 5 times 1 gives me that negative 5 there. So I have two proposed solutions. 4x minus 5 equals 0. X plus 1 equals 0. I'm proposing that either x is 5/4 or x is negative 1 or both. Now I've got to think about if these are both going to work, so I'm going to go put them back in, and I see immediately, you know what, that negative 1 is extraneous, because that would give me a negative argument. So my only valid solution is the 5/4. Alright, number 6. I have two log statements on opposite sides of my equation. That's all I've got going on, and they have the same base. This is a great opportunity to use our one-to-one property. The log statements are the same. I can say that the arguments are equal, and then I just solve for x. And one last equation to work through. Again, I've got two log statements on the left. Subtract, so I'm going to use my properties of logarithms. Subtraction pairs with division. So I've got log base 2 of x plus 9 over x equals log base 2 of x plus 1. And now I have a single log statement on each side. They have the same base, so now I can use my one-to-one property. One-to-one property says if the logs have the same base, then the arguments are equal. So x plus 9 over x equals x plus 1. Remember, our go-to move here is to multiply both sides by the denominator. On the left, that gives me x over x is just 1, so it leaves me with x plus 9. On the right, I need to distribute that, so I have x squared plus x. Now this bit is quadratic, so I need to set it equal to 0 by moving these values over to the other side. So 0 equals x squared. X minus x is 0 minus 9. Now, why did I move everything to the right this time? Well, I need to keep my squared term positive. This is going to be difference of squares. I can factor it, or I can use square root property. Let's go ahead and factor it. Difference of squares factors to give me conjugate pairs. Get the same result either way, it's just a different way of looking at it. And then my zero factor property says that if I'm multiplying these together and get 0, that means that one or both of them has to be equal to 0. So I solve and I get proposed solutions, -3 and +3. I have to think about checking those back into each of my arguments. +3 is going to work in all three. -3 works here, but it does not work there or there. So that's extraneous, and that's my only valid solution. Alright, one last example, an application problem. The total revenue for CVS Health in billions of dollars can be approximated by this function, where x equals 7 corresponds to the year 2007. So x equals 0 would be 2000. I see that my variable is in the exponent, so this is an exponential function. Well, we know the shape of an exponential function, right? It's got that curve, that exponential increase or decrease. Is this one going to be a growth function or a decay function? Well, I've got this positive coefficient, positive base. It's e is equal to about 2 is over 2, so that's a whole number. So that means it's going to be growth because that base is greater than 1. I've got this constant here that's going to mean this goes up steeper. Identify and interpret the y-intercept. The y-intercept happens when x is 0. So f of 0 41.6 times e to the 0.088 times 0, anything times 0, 0, e to the 0 is 1, so that is just 41.6. So there is my y-intercept, 0, 41.6. It tells me to interpret it though. Well, x represents years, so in the year 2000, CVS Health brought in total revenue billions of dollars, so 41.6 billion. That was their total revenue in the year 2000. Use it to sketch the graph. Alright, so let's think about this. If 0 is going to be the year 2000, my y-intercept is at 41.6 billion, in billions over here. And we know that this is an exponential function, so it's going to go like this. What was the total revenue in 2011? Well, we could use that as another point on our graph for 2011. F of 11. My exponent is 0.088 times 11. You plug that into your calculator, find that value, x to that value, and then multiply times 41.6, you get 109.5. And again, that's billion. So when that comes out here, that's going to hit at 109.5. That's messy, 109.5 billion. Where x is 11. That was the revenue in 2011, that's C. What was the first full year in which the revenue exceeded 140 billion? So I'm looking for the year when my revenues, 41.6 times e to the 0.088x, was greater than 140 billion. Well, let's divide out this coefficient. So we've got e to the 0.088x needs to be greater than that keeps going. Let's round it off. Let's keep 4 decimal places, 3.3654. How am I going to solve this? My variable is an exponent, so I'm going to use my definition of logarithm and write it as a log statement. Base e gives me natural log of 3.3654 greater than 0.088x. Oh, no, wait, I think that's going to need to be this. I just got my, when I switched, no, I think we're okay. We'll check it out when we get to the end, see what makes sense. So we need to divide both sides. So natural log of 3.3654 divided by 0.088. I think that needs to be greater than. We're going to check that out. I think that I've got my inequality on the wrong side, and I'll talk to you about how we can decide if our inequality symbol is written down the right way or not. So natural log of 3.3654, I need to divide that by the coefficient 0.088, and I get 13.79. So 13.79. Now, this is year because it's an x. If I turn this around, it would say x is less than 13.79. I need to know what year it is greater than. Notice, so here's what I did wrong. I switched my inequality symbol without keeping it oriented to the variable. That's where I messed up. So let's fix our inequality symbol. My original statement was great, and this statement was great. I've got x greater than, and then down here, when I rewrote, I moved my x to the other side of the equation and I didn't adjust my inequality symbol. So when I rewrote from exponential form to log form, I put my x over here. It should be open to the x. So this should be what my inequality symbol looks like, open to the x all the way down. So I'm looking at the year greater than 13.79, so it would be x would be 14. The first full year in which it's greater than that would be 2014. Now again, just another quick recap of what I did wrong with my inequality symbol. When I set up my equation, I was in good shape. I've got this value greater than 140. The variable is over here being greater than something. Right here, I'm in good shape. My variable greater than something. Then when I rewrote from exponential form to log form, the way I rewrote it, I put the variable over here on the right. Well, I should have kept my inequality symbol oriented the same way to my variable. So it should be x is greater than whatever's on the other side.